Thank you. To understand the autonomous features effect, we first need to understand a few things. Firstly, we need to understand what the base vehicle model operation looks like. We need to know what the base battery heat loads are, what the base motor heat loads are, the battery power consumption, and the motor battery consumption. And we also need to know what the base requirements for the vehicle are. Secondly, we want to know what the autonomous driver means for a vehicle. How do we define an autonomous driver when it comes to impacts on the vehicle and when it comes to modeling, and what this impact of this autonomous driver would be on the vehicle. And then thirdly, we want to look at this effect of the autonomous driver across a bunch of real-world drive cycles. And so for that, CSEG developed a few different real-world driving cycles in and around Ann Arbor, and we'll discuss that in more detail. And then once we've figured out what the impact of the autonomous driving features would be on the vehicle, then we can then start to see what it would mean in terms of design changes. And for that, Doug will cover what the impact of these autonomous driving features will be on the load time circuit and the airflow required for that. So this whole approach that we did for the analysis was a computational approach. And we used two major tools for that. The first one is PowertrainLive from CSEG. And PowertrainLive is a forward-looking, high-fidelity vehicle simulation model. It simulates fuel economy, battery range, and also the thermal and performance behavior of different components. And I'll talk a little bit more about PowertrainLive in a second. And the second tool that we used was Flowmaster, and that is a 1D CFD tool for internal flow and thermal transient modeling. And we used Flowmaster here to model the load time circuit for the Chevy Volt and to understand what the impact on the air side. So let's talk about the baseline vehicle model development first. So the vehicle model development was done in PowertrainLive. PowertrainLive is a high-fidelity, forward-looking vehicle simulation software. And there are a few things to note about PowertrainLive. Firstly, it is a forward-looking simulation software where teams can use to simulate fuel economy impacts and driving range impacts of different vehicles. But things to note here are that PowertrainLive actually comes with a few standard models. So there's standard models on conventional powertrains, such as Ford F-150, Dodge Ram, smaller cars such as Ford Focus, hybrid powertrains, plug-in hybrids such as the Chevy Volt, and also electric vehicles. The CSEG team went above and beyond just developing the software, but also spent significant amount of time collecting the data on these vehicles and correlating these vehicles to transient dynamometer data, so that when our customers start using PowertrainLive for what-if studies, they have a correlated model to start with, and don't have to spend months of time basically developing a baseline vehicle model. The second thing to note on PowertrainLive, it's actually deployed on the cloud, which means that there's no software to install, no IT departments to deal with. Anyone with an internet connection in the browser can access the software fully. The entire software is developed in Java and can be accessed through the browser. And this means that global teams and teams in different locations can log in at the same time and work on the same models and share the design iterations among different offices. And the third thing to note on PowertrainLive is that it has fully open APIs, and this means that PowertrainLive and its standard vehicle models can seamlessly co-simulate to any of the CAE tools. So that's PowertrainLive. For our study here, we picked 2016 Chevy Volt. So why did we pick the Chevy Volt? Few different reasons. First of all, it's a plug-in hybrid, so the battery is large enough to run in a pure EV mode. So in the event that we wanted to see what the impacts were on an electric vehicle, we can simply just run this vehicle model in an EV mode and understand the impacts that any technology or feature will have on an EV. And then secondly, as far as the hybrid technology is concerned, the Chevy Volt, the 2016 Chevy Volt, this is Gen 2 and is one of the latest developments in hybrid technologies with 2 planetary gears and 2 motors and a 1.4 liter IC engine. And so the 2 planetary gears give it 5 different modes of operation, 2 of them being EV modes and 3 of them in hybrid modes. So it's quite a diverse and complex model to develop, and would also represent the state-of-the-art hybrid vehicle for us to evaluate different technologies on. Let's look at a couple of different major subsystems inside the Chevy Volt for us to understand the thermal impacts and the autonomous driver impacts that we will be studying. The first one is the battery model. The battery model was represented using an RC representation. So each individual cell inside the battery is represented with an open circuit voltage and 2 different resistances, R0, R1, and a capacitance C1. And each of these parameters, which is the voltage and the resistances and capacitance, are a function of state of charge of the battery and the temperature of the battery. And we extracted the battery performance as for the complete range of state of charge, all the way from fully charged, 100%, down to about 20 to 15%, where the engine actually kicks in into a charge sustaining mode and doesn't let the battery go further down from there. So here are a couple of examples of what the performance maps look like. You can see the open circuit voltage of an individual cell in the battery on the right side. You can see that the voltage is anywhere between 3.5 to about 4 volts, and the 2 independent variables are state of charge and battery temperature. You can see that the voltage drops slightly with battery temperature going down, and the voltage drops quite a bit with state of charge coming down. And then the same thing on the resistance as well. If you look on the left side, it's a function of battery temperature and state of charge as well. And with these performance maps, actually the battery does exceptionally well in both the steady state and transient scenarios. So if you look at the correlations of how this battery model predicts against test data, you will see that the correlation is actually really good. The blue line is test data, and the orange line is simulation data. And the middle graph on the left side is the predicted voltage for the battery, and all the way in the bottom is the state of charge. And the top graph shows the blue line, the current demand for the US06 drive cycle. And we're showing the US06 drive cycle here because it's a very aggressive drive cycle and a highly transient drive cycle, so we wanted to see how the vehicle model did, or the battery model perhaps, did in correlation. And you can see that it does do a pretty good job in terms of capturing the transient of the battery voltage and state of charge changes. The second big submodule to look at is the driver submodule. This is critical because we are particularly interested in looking at the autonomous driver influence on the vehicle. The driver model uses the drive cycle as the input, the road conditions, the grade, and a few other parameters for the controller itself. But the driver model is quite complex. It's a combination of a PI controller, a forward-looking smart driver controller, and also sort of a feed-forward looking controller, which looks at the complete backward-looking vehicle model to determine what the pedal position would be. For our study, we actually also inserted an autonomous driver influence into the accelerations, but I will talk about this in a little bit more detail in a few slides. So with the battery model and the details for the motor efficiencies and all of the other submodules modeled, the overall vehicle model correlation actually was really good compared to the test data. This graph shows different parameters for the current, state of charge, voltage, motor speeds and torques with the simulation compared with the test data. And we correlated the vehicle model for multiple drive cycles. So we did it for the UDDS hot start, cold start, the highway drive cycle, USO 6, and also FTP cold, which is the -7C start for the UDDS drive cycle. And we ensured that the vehicle model worked pretty well across all temperature and acceleration zones. And here is a little bit more zoomed in picture of the exact same correlation, just so we can see how the model did in terms of capturing the peak currents and peak voltage changes and peak torque changes. And this is particularly important because we are interested in the battery heat loads, but also the peak heat loads, which will be a function of the current. So that was our baseline vehicle model, and with that we'll then look at the influence of autonomous driving features. So the first question is, how do we represent connected and autonomous driving? There are three key things that we considered. The first thing was smoothing of the speed. So with adaptive cruise control and intelligent speed adaptation technologies, we would expect that the driving profile would be a bit more smoother than the current driving profile. So that's thing number one. The second thing to look at was limiting maximum acceleration. And this is either perhaps due to safety or for eco-driving. The maximum acceleration of the vehicle will likely be limited. So as an example, the picture shown here is a fully autonomous shuttle that will run in Ann Arbor starting fall 2017. And even though the vehicle can reach up to 28 miles an hour, it will likely be limited to about 15 miles an hour, mostly because of the conditions it will drive in and for safety. And the third thing is removing the stops. We would expect that as the autonomous driving features get more advanced, and looking forward, we would expect vehicle-to-infrastructure communication leading to elimination of some of the stops. So with these considerations coming into connected and autonomous driver, we wanted to see what the driving profile change was and what the impact was on the battery and the motors. So on the graph on the left, you would see the black line is the driving profile with a human driver. This is one of the real-world drive cycles that we collected in Ann Arbor. And the green line shows what the driving profile looks like for the connected vehicle. And so the top graph obviously is the vehicle speed, and you can see that the drive cycle is a lot more smoother, and a couple of the stops have been eliminated. The second thing also at the bottom, you would see the battery power consumption, and you would see that the battery power consumption actually has reduced by about 16%. So what does that mean in terms of heat loads of the battery and the motor? If you look at the bottom two graphs, the black line shows the battery heat load with the human driver, and in the bottom graph, it's the motor heat load with the human driver. And the green line shows that the heat loads with the connected vehicle driver. So you'd see that even though the vehicle driving profile is similar, a lot more smoother, but similar, the peak battery heat loads for both battery and the motor come down quite a bit. So we're seeing a 41% reduction in motor heat load and 66% reduction in the battery heat loads. So the question is, what degree of smoothing would we really see in the autonomous driving vehicles? So we actually did a sensitivity study of 4 different cab driver profiles, as we would like to call it. These are differing degrees of limiting accelerations and smoothing the velocity profiles. And we find for each of these driving profiles that the battery consumption's coming down proportionally. So 2.1 kilowatt hours come down to 1.8, 1.6. I think this is similar to what we had just seen. But what is surprising to note is the peak heat loads. So if you look at the baseline heat load for the motor, it's 35.1 kilowatts. It's dropped more than 50% down to 13.9. And the battery peak heat load dropped drastically, more than 80%, down from 21 kilowatts to about 3.6 kilowatts. So there was a drastic reduction in peak heat loads and a pretty moderate reduction in cycle average heat loads. So the question is, why is there such a drastic reduction in battery heat load? And the answer to that is in the first principles of how the batteries work. The battery heat load is due to the resistance inside the battery, and the heat load is a second order function of the current. So as our current demand drops, the battery heat load drops by the square of the drop in the current. So the heat load drops significantly. And we see that the motor heat load is actually a linear function of the current demand. So with that drastic drop in heat loads, we asked ourselves the question, well, is this effect just for that drive cycle that we picked, or is it actually prevalent across multiple drive cycles? And is it representative of, in general, driving? So in summer of 2016, CACG collected about 58 real-world drive cycles in Michigan, in and around Ann Arbor. And we picked a few of these drive cycles to evaluate the effect of this cab driver. So we used a measure called the positive kinetic energy, and we evaluated the drive cycles for the positive kinetic energy. And so we looked at how the positive kinetic energy changed for different drive cycles with different average speeds and different driving distances. And we picked 5 different drive cycles with changing distances of driving and average speeds to analyze what the effect of the autonomous driving features would be. And these are the 5 different drive cycles that we picked. RWDC1 is real world driving cycle 1, 2, 3, 4, and 5. And 1, 4, and 5 are city driving conditions. And we actually find a decent drop in the battery power consumption, around 30% drop. And RWDC2 and 3 are highway drive cycle. And that means that if you look at the graph on the right side, the black line is the human driver driving profile, and the green line is the autonomous driving profile, with limiting accelerations and smoothing out the velocity profile. Still, you can see that it actually follows the drive cycle pretty closely, and therefore the reduction in battery power consumption is lower for highway, as opposed to for city on the bottom left, where smoothing out and limiting the accelerations is much higher. And when we look at the peak heat loads, the story remains the same. Whether it is a city driving cycle, which is RWDC 1, 4, and 5, or highway driving cycles, the peak heat loads drop by quite a bit, 70 to 90% drop in peak battery heat loads, using the connected and autonomous driving features. So to summarize the thermal impact of autonomous and connected driver, we find that the battery power consumption comes down by about 18%, with highway being about 7% drop in power consumption, and city driving can be anywhere between 16 to 33% drop in battery power consumption. But when you look at the heat loads reduction, you would notice that there's a drastic reduction in heat loads, almost 60 to 80% reduction in battery heat loads, and the peak motor and battery heat loads have been reduced by quite a bit. And this is primarily because of the reduction in currents and accelerations of the vehicle. So with this big reduction in peak loads and cycle average heat loads, we want to now find out what does this mean in terms of design of other subsystems in the vehicle, such as the low temp cooling system. And to look at the influence on low temp cooling system, I will turn it over to Doug.
Thank you very much, Sudhi. So now I'm going to take you through a few scenarios we looked at to see how the autonomous driving would influence the low temperature cooling system. So if we look at what a low temperature cooling system looks like, in this particular case for the Chevy Volt, here's a diagram. If we start on the top, we start with the electronics radiator flowing down into the power inverter module, so it's having the cooled coolant being delivered to it, as well as the motor. From there through the air separator and being pumped by an electric pump. Finally around to the plug-in charger assembly, then closing the loop back to the radiator. For what we're looking at, based on the numbers we saw in some of the previous slides, we're going to be looking at a combined power inverter and electric motor for heat generation. And we're going to assume 8 liters per minute in coolant flow rate. We want to target a main power inverter temperature below 60 degrees C, so that's sort of our cutoff value. If we look at what the model looks like in Flowmaster, you can see it here on the right-hand side. It has been rotated 90 degrees. One thing to note is we have excluded the plug-in charger assembly. The reason being we're running drive cycles, so we're not actually going to be charging the vehicle during any of these, so it was just an unnecessary component. We did size the pump to deliver the 8 liters per minute for the given system pressure drop. We did account for the pressure drop of the plug-in charger assembly in the piping. For the power inverter and the motor model, again, we're doing that as a combined set of components here using the solids components. In particular, a heat flow rate, a lumped mass for the thermal inertia, and a thermal bridge. Again, the reason we wanted to do this is to be able to capture any sort of thermal capacitance of those components. And to model the radiator, what we did was use a thermal performance map that we were able to get for the Chevy Volt radiator in terms of effectiveness versus the mass flow rate of air through it, as well as the mass flow rate of coolant through it. So the scenarios that we're going to look at are basically the 5 that Sudhi just finished talking about. For each of those drive cycles, we obviously had a human option and an autonomous vehicle driver option. We're going to look at 3 different airflow settings. So the first is going to be with the AGS closed. This is going to deliver the lowest flow rate of our 3 options. The next option is if we're not getting enough airflow rate, we can open the AGS and get more flow. The final option is if that's still not enough, we can keep the AGS open and then we could turn the fan on, which will give us our maximum amount of flow rate. It is important to note here on the right hand side, all of these flow rates are based on vehicle speed. So you're generating that ram air. The higher speed you're going, the more flow rate you're going to get to the radiator. So with that in mind, in these scenarios, we have 2 questions we want to answer. So the first is, if we just use a standard human driving model, what is going to be the airflow that's required for each of these scenarios to keep the power electronics and motor below 60 degrees C? Once we've established that for a given scenario, we want to look and see how much can this airflow be reduced if we use an autonomous vehicle driver. So let's start by looking at real-world drive cycle 1. If we look at the top over on the right, what we can see is the airflow rate versus time. And as I mentioned, this is a function of the speed, so you can see that it closely follows what the drive cycle looks like from the real-world drive cycle. And in the blue is the human driver. So it's a much more jagged, much more acceleration and sharp deceleration involved, where in the red, you can see the autonomous driver has smoothed that out, not only in the drive cycle, but that gets reflected in the airflow rate. So if we think about the human driver first, and we start again with the AGS closed, the first thing we need to find out is what's our max temperature. And so here we can see it's 49.1 degrees. That's well below the 60 degrees that we required. So we know that using the AGS closed will be acceptable for the human driver. In general, it means an average airflow of about 73 CFM. So what we can then do is apply this to the autonomous driver. And as we'd expect, we could stay with the same AGS closed, and we're going to get a reduction in temperature, mainly because we have less heat being generated, as we talked about earlier. So really a temperature difference of about 12 degrees while having a lower flow rate, which is an interesting part to this, because generally if your airflow goes down, you'd expect your temperature to go up, but there's so much less power being generated, we still have a good temperature drop. And in fact, an airflow reduction of almost 13% still results in a low temperature coolant reduction of 16 degrees C. So in terms of real world drive cycles, we're fine with our airflow rates either with the human driver or the autonomous vehicle, but we can see even with a reduced airflow rate, we're still going to have a significantly reduced temperature. So if we look at real world drive cycle 2, this becomes a little bit more interesting. So we'll start specifically with the human driver, again with the AGS closed. So if we run this analysis, we'll see that we get a max temperature of 79.8 degrees, so almost 80 degrees, far higher than the 60 degrees C limit we set. In terms of the airflow rate, we ended up with an average of about 309 CFM, with our peak flow rate close to 400 CFM, and during the highway portion, really sitting about 375 cubic feet per minute. So if we go ahead and we open up the AGS, we're going to increase our airflow rate, and in fact, from an average perspective, we get up to 465, and our max goes all the way up to 600 CFM before settling around the 550, 560 mark during the highway portion. And this does reduce our max temperature significantly, but it is still above the 60 degree requirement that we have for these parts, which means we have to look at turning the fan on. So this, once again, increases our average flow rate by about 200 CFM to 656 CFM, really sitting around 800 for most of the highway drive cycle. But it does reduce our max temperature down to 59.6. So we have been able to meet our design requirements with the AGS open and the fan on. Since we've established what airflow rate we're going to require from the human driver, now we can see if, with the autonomous driving features, we can reduce that slightly. So if we start with the same configuration, so the AGS open with the fan on, what we'll see is our average flow rate really doesn't change that much. The reason being, this is predominantly a highway drive cycle, so all of that sharp acceleration and deceleration, especially at the high power requirements, is really negligible. So we're very small reduce our airflow rate to start. And we do of course see a lower temperature because we have a lower heat load due to the autonomous driving features. With that reduced temperature, it gives us the opportunity to perhaps look at turning the fan off. And so that was the next step. If we reduce that, so we just have the AGS open, we have a fairly significant reduction in airflow down to 463 CFM, and we're still able to maintain a temperature under the 60 degrees C, as you can see here at 58.3. So doing this, this is one area where the autonomous vehicle had a significant reduction in airflow at over 29%. So that's really going to help us. And not only does it mean a reduced airflow, so hopefully an improved drag coefficient, it also means we don't have an electrical component turned on. So that's going to save us, while it might not be a large amount, it is going to save us some power in terms of running that fan. If we look at real world drive cycle 3, it's going to again be very similar to real world drive cycle 2. We were not able to maintain the proper temperature for a human driver until the AGS was open and the fan was turned on. In this case, we even had a higher airflow rate requirement than rear-wheel drive cycle 2 at 707 cubic feet per minute, but our max temperature was slightly less at 57.2. Again, we were able to reduce our airflow settings with the autonomous driver by turning the fan off. Again, reduced the average flow rate by over 200 CFM, and we were still able to keep that max temperature under 60, even though there was a 1 degree increase in this particular case. And again, airflow reduction at about 29%. If we look at rear-wheel drive cycle 4, it's similar again to the first one we looked at, where with both the human driver and the autonomous vehicle driver, we were able to keep the AGS closed and easily maintain temperatures at the power inverter module and the motor far, far below the 60 degrees C. That being said, by using the autonomous vehicle driver, because of the reduced aggressiveness in the acceleration deceleration, we still did end up with a airflow reduction of almost 11%. And again, we were able to do the same thing with the rear-wheel drive cycle 5, keep the AGS closed for both conditions, and again, max temperature was well below the 60 degrees C. This particular case, due to the shape of the drive cycle, our airflow reduction was not quite as high, at only a 5% reduction. So I'll give you a summary of the impact of the autonomous driver on the low temperature cooling system. We did see significant reduction in airflow requirement both for rear-wheel drive cycle 2 and rear-wheel drive cycle 3, as we can see here at over 29%. For both of those drive cycles, again, not only could we shut off the fan, which reduced the airflow, it also meant that we weren't running an electrical component. We also realized that there's actually further opportunity for refinement here as well. Some of the assumptions that we made were that the fan only had a single speed. It's much more common for these auxiliary fans to be able to have variable speed. Also, we looked at the AGS as either open or closed. These are components where we could have 3 or even 5 different positions if we felt that that was warranted. Also, with each of these drive cycles, it was always in the same position for the entire drive cycle. So the AGS always either started open or started closed. It didn't open at a given point when we felt it was necessary. Same with the fan. It either started on or started off and stayed that way for the whole thing. Implementing some sort of a control algorithm would obviously give us the ability to further improve our overall temperatures. So hopefully in today's webinar, you were able to see a couple interesting things with autonomous vehicles, and there's several key takeaways we have. First, the high-fidelity forward-looking vehicle model of the 2016 Chevy Volt. It's extremely useful in understanding the influence of various technologies, in particular, autonomous driving features. We saw how using autonomous driving helps to reduce the overall battery consumption in some standard and real-world drive cycles, basically by reducing the acceleration and deceleration that a human driver would experience as part of their standard driving. We also saw that it was able to substantially reduce the battery heat loads and motor heat loads, again, for the same reason. In terms of our cooling system and how that applies to that, we looked specifically at the low temperature cooling system. And we saw that we could get significant reduction in inverter and motor heat loads, which meant we needed significantly reduced airflow to maintain the temperatures required. In some cases, up to 29%. And these autonomous drivers also minimize the need to engage auxiliary cooling fans, which can help to improve your drive range as well. With that, I'd like to say thank you on behalf of myself and Sudi for attending the webinar, and turn it over now to questions.